Okay, yeah, so I'll talk about that later again before we start. So now let's kind of finish up our remaining slides on compound processes. Okay, so we have covered almost all the processes on the compound and hybrid and assisted machining processes. Okay, so this one is a sequential laser and ECM process. So today's first process was laser and the ECM, but that was a hybrid process, right? Where like both laser and the ECM jet was removing material at the same time. But this one process at a time. When laser is working, ECM is not working. When ECM is working, laser is not working, right? But remember, in sequential process, you can also, it doesn't need to be like one process after one process only. So you can actually just change them as many times as you want, right? So you can use laser, then ECM, then laser, then ECM again. So as long as you are using those separately, then it is a kind of sequential process. So the goal, we know that electrochemical machining is good for surface finish, right? It gives you good surface finish, but we also know the challenges, right? The profile accuracy is a challenge, and sometimes controlling the dissolution rate is a challenge. So if you really, like don't cover any part, it can have electrochemical dissolution from that part, right? So that's the kind of the goal here. So on the other hand, for laser, you know that laser is a faster process, but it creates some kind of heat affected zone, right? So how you can actually, use both processes one after another and, improve the overall process. So this is slightly interesting process. It is like laser is not used for material removal here, okay? But it is an interesting process. Laser is used for some coating, some oxidation, so that electrochemical dissolution, doesn't take place there. So let's look at the process mechanism. So the process is done in 4 steps: anodizing, laser masking, electrochemical dissolution, and ultrasonic cleaning, right? So the first thing, like for example, you start with the titanium, and titanium has a tendency, actually titanium, aluminum, all of them, they have a tendency to form oxide layer. Even like for example, titanium is not very chemically reactive, but still, like especially aluminum, if you take aluminum block, keep it for some time, it will have very thin layer of aluminum oxide on the surface, right? So for titanium, what you can do is you start with the titanium and then you do some anodic oxidation for oxide layer. Okay. Now, why you need to put some oxide layer? I don't know. Is it from here? You control it? Okay. So we know that one of the challenge of ECM is unwanted electrochemical dissolution, right? So anything that is exposed, like for example, you are machining in this area, and anything that comes into expose, it will be uncontrolled dissolution. So how we control that? That's what the goal of this. So the goal is you will machine this, right? But before machining, you kind of create a protective layer. Then that protective layer is a little bit difficult to machine. So you use laser to kind of do some pilot hole for that protective layer. Then you do the electrochemical dissolution. So that the layer that you protected, the material that you protected, will not go through electrochemical dissolution. So that's kind of the goal of this project. So again, let me say there are 4 steps. First step is anodizing. So that means you have a metal part, you create a protective oxide layer by anodization, oxidation. Second, because that oxide layer is difficult to machine, you use a laser to kind of penetrate that oxide layer and create the channel or path for the electrochemical machining to happen. Then the electrochemical machining will go and remove the material based on the cavity that you defined. It will not remove material in other place, right? You have that protective coating. And then once it is done, you do some ultrasonic cleaning also. So here, so first step, you start with the titanium, then you put some oxide layer on the titanium surface so that it is kind of protected. Then you put some, that excimer laser to create the path for the electrochemical dissolution. Then you kind of, do the electrochemical machining, and you see there is some dissolution. And then the remaining oxide layer, if you use some ultrasonic cleaning, that remaining oxide layer will chip off, but the other portion will have that oxide layer as the protective coating. Then you actually finish the process. So this is kind of the process mechanism for this process. Okay. So here the laser is used slightly for different purpose. Okay. So how that can be useful? Remember, this process works very similar as the LIGA. In the LIGA process, right, we use some, or maybe ECDM process, we use some mask to control where we don't want any kind of machining or deposition to happen, right? The machining or deposition will happen only in the exposed area. So here we are putting the mask using the anodization process, and we are using laser to create the channel where the machining is happening, right? And then once the machining is done, then you use ultrasonic cleaning to remove some of the remaining like oxide layer. So for here, the first picture in the inset is the masking. So that means you are using anodization, okay, to put the complete layer. Then you use laser to create the channel where the machining needs to be happened, right? So here you see, you put some masking, okay, some portion is open and some portion is not open, so those portions are protected by the oxide layer. And once you have the mask ready, that okay, I would like to have the machining in those areas and other portion will not be machined, and then you kind of do the electrochemical dissolution. So here I think those black cavities, the electrochemical dissolution happened, and some portions the electrochemical dissolution was not happened because those portions were coated first. Does that make sense? So that's the compound process here. So challenges, the reliability of laser beam masking being an issue. Okay, so this is not used for 3D sculpture machining. So if it is a plain surface, it's an easy process for laser. But if you have some complex cavity or sculptured, like for example surface, then it becomes a challenge. But again, it doesn't need to be this process. You can think of how you can use another process to put that protective coating. Like LIGA, they use electroplating, right? So electroplating is another way that you can probably get rid of that and do the protective coating. And the performance can vary based on the capability of the laser to fabricate insulating oxide, that will work as a mask. So okay, very similar here, sequential laser machining and milling. So what I meant, like for example, you want to make a complex features. Some part needs to be very thin channel, right? And some part needs to be comparatively thicker channel. So if you have thicker channel, you use the laser itself. For all thicker and thinner, it will be very expensive. And in addition to being expensive, laser will leave lots of heat affected zone, recast layer on those channels. So how you can resolve that? So you will leave only the critical dimensions and some micro channels for laser to take care of it, and other parts you will do machining by the milling process, right? So that's what the sequential machining and sequential laser and milling process. Then definitely this will be much faster, and also more importantly, it will be much cheaper than using the laser process itself, right? And milling process will definitely give better surface finish than the laser process. So here, the process mechanism. So sequential process in a single machine, combining micro milling and micro laser, it will be economically efficient, as I mentioned. Accurate positioning and alignment is very important. So that means if you are doing that, the equipment that you are using should be very accurate, because the axis resolution, movement of the axis plays a major role in the accuracy, right? So look at here. So here you see these parts are machined, right? Some parts are machined. These parts are, so this is laser machining, then this is milling, right? So some part is milling and some part is laser machining, but again, this process, you need to face some challenges. I think definitely they were facing some challenges for using laser to machine some of the parts, and that's why they come up with that. Okay, if not, I don't think you should just remember. That's why I will ask you to, when you select any combined or sequential process, you need to tell how that would be beneficial than individual processes, right? You cannot just create the process, even for research, you need to show your process is better than the other two process. So micro milling, definitely faster process, but it cannot really go very small. On the other hand, laser, it can go very small, but it's a slower process and it has heat affected zone. So you combine both. And definitely here it shows the machining time. So you have milling, that is higher machining time, slower machining time, laser machining, which is very fast. Then you combine both process, which is kind of the gray line, right? So it just follows the path, right? It just follows the path of the two processes. But I think overall machining time should be reduced, because you are actually, like taking out some of the portion of the laser or milling. So here it shows it very well. So you just mark, okay? So the laser machining will be the darker. So you see this corner. I have the pen here, right? So here you see, this is a portion challenging to machine. This is a portion challenging to machine, right? Then here also, this is a portion which is challenging to machine. So you identify which portions are challenging to machine using the milling process. Then you select those for laser machining, and remaining, comparatively larger sections, easier to machine section, you identify that you are going to do the milling process, and then you just machine using the milling and the laser process. Okay. So but the laser process will end up with some tool mark, as you can see here. On the other hand, milling process, but the laser process will also have some heat affected zone. Okay, but at the end, you should be able to kind of get the part at comparatively faster speed and with less defect. So that's the kind of goal here. Okay. Yeah. So here also, this is another area difficult to machine using the milling here. So those areas can be really like machined by the laser. Okay. Yeah. So challenges, the accuracy of the process is determined by the axis resolution, as I mentioned. So it's kind of the accuracy is dependent on the machine that you are using, and it will have varied surface finish, right? As you can see from here, there are differences in the surface finish here. Sorry. There are differences in surface finish here and here, right? Same, yeah. So there will be some differences in the surface finish in the laser and milling portions, and also Yeah, so matching surface finish is needed. So there are some scope for improvement in this, but I don't think this is, there are lots of innovation here, but definitely it can be an effective process, you know, especially for MEMS and NEMS applications. Okay, next one, sequential mechanical pack drilling and reverse CDM. So remember, how many of you have done reverse CDM? Yeah, so reverse EDM, how it works, I remember in one slide I showed, right? So you use the EDM process to drill holes, okay? Now EDM can drill one hole at a time, right? So if you have to machine 100 holes, so you are machining 100 holes using electrode, and the electrode that you fabricated and that has you eliminated the spindle run out, maybe you used for 10, and then you need to change the electrode again, do the dressing again. So it's a lot of time consuming process for both electrode dressing and also machining the holes, because the machining time will be just multiplied. So there are several ways, you know, in industry, there are several ways of fabricating electrode, right? You can use like for example wire EDM, if it is a square or rectangle profile arrays of electrode, wire EDM is a very effective way. We saw Liga, if it is, you know, not like uniformly circular or rectangle, you can use Liga, but Liga has its own limitation of aspect ratio. So reverse EDM is another process. Is we know that in EDM, if you change the polarity, you can control which electrode has more material removal, right? So for example, when you are doing micro EDM or EDM, we select polarity so that there is more material removal from the workpiece and less from the tool. Now, if we want more material to be removed from the tool and consider that as a workpiece, we just reverse the polarity and more material will be removed from the tool. So reverse EDM is, like for example, you want 10 by 10 arrays of electrodes. So first you use to make 10 holes. Now, if you use EDM, just what I showed in one of the slide, if you just use EDM to make 10 by 10 holes, you are still, even for the first batch, you are spending a lot of time to do that, because EDM is a slow process. So that's why the mechanical pack drilling comes. Okay, so mechanical drilling is a faster process, right? And sometimes if you do full drilling, maybe you can damage the profile. So you can do some pack drilling to get the arrays of holes, and then you do the reverse EDM. So for the reverse EDM, like for example, your workpiece will be as a sacrificial electrode. So most of the cases we use foil, thin foil, okay? And then I have another electrode with some arrays of holes that is going down. So when it is going down, remember, like where there is a hole, so it works like a mask, right? Where there is a hole, it can go into there and the electrode will come out from the hole. And where there is no hole, there is a two electrode facing each other. So material will erode just like the EDM does. Okay? So the portion where there is no hole, material will be removed, okay, from the workpiece, from the aluminum foil. But because we select the polarity in such a way that material will be removed mostly from the tool, so the portion where there is no hole, it will become cavity, and when there is a hole, there will be no machining happening, so that electrode will go. And at the end, you will end up with electrode where there was a hole in the mask in the workpiece, and other portion will be cavities. So it can give you very good, reverse like micro EDM can give you very good arrays of electrode. But remember, in the reverse micro EDM portion, the itself is a slow process, but machining the arrays of holes is the slowest one. So if you can at least get rid of that, you can improve some machining time. So that's why the pack drilling process is happening. So you are using a tool to kind of make the hole using the pack drilling first, okay, and then once you have the arrays of holes, and then you can do some reverse EDM process to make the electrode. So So that's kind of the goal of this process. So here you can see, so you use some pack drilling to arrays of holes. Now if you want to use EDM to make that many holes, you will spend forever, right? Micro EDM especially. So you can use pack drill, which is mechanical drill, to machine all those arrays of holes, entrance and exit side, and then you can use some reverse EDM to get those arrays of electrode, right? Very cool, right? You can, from here you can get those arrays of electrode. So it's a cool technique, but so this is photos of micropin arrays, and you see those are not very uniform, right? Not very uniform. So what you see in the middle, the electrode size is smaller, and in the at the edge or outside the electrode side are mostly smaller. So the flushing process plays a major role here, because where like it is difficult to remove the debris from those center rows. Okay, so there will be more wear, in those portions. So, but overall, if you look at the arrays of electrode, that's very good. Okay, and you can see some taperness. This is just because of when the reverse EDM is going, at some point there is wear from the plate electrode also. Remember, you have plate electrode, which was previously workpiece, now becomes pseudo electrode. So you have plate electrode with arrays of holes, and you have a plain electrode that is going down, and it will end up having those arrays of electrodes. And other portions, machining could not happen because of the plate. But as the machining goes, the hole in the plate is also extended, right? So that's how you see taper. So remember, in the arrays, this portion, this is portion machine first, right? And this portion machine last, right? So when this portion was machining, already there are some wear in the plate electrode that make those holes larger. So that's why you get those taper shape. But that is good because it gives some support to those arrays of electrode. Okay, if you don't put support, in the electrode, yeah. So you remember yesterday, Prof. Raman also talked how he obtained 50 micron, electrode using turning. I think we covered that in the very first day, right? When we talk about compound machining, you need to have some kind of support at the beginning. Otherwise, it's very easy to kind of break when you are doing the turning. Similarly here also. So I think this is a cool process, and there are several ways of doing that, but definitely mechanical pack drilling would be very useful, especially circuit board. Circuit board, there are a lot of research going on how you can get lots of holes in the circuit board, right? So mechanical pack drilling is used there, but they use the same concept with reverse EDM to get the arrays of electrodes, right? So, and I think this is a cool research. Okay, I think this is the probably last one, laser and mechanical micro drilling. So we know that laser is a faster process, right? So if you use a laser to make a pilot hole, and it will be smaller hole, but there will be a lot of recast layer, right? And you can use some mechanical drilling to remove those recast layer. But again, we used ECM process to remove those recast layer. So mechanical drilling, if it is difficult to cut material, probably not a good option, right? ECM would be good option. But if it is comparatively easy to machine material, but deep, right? Then you can do laser or maybe incline, not deep, incline. So if it is inclined, it's sometimes difficult to machine also. So you can use laser to make the pilot hole, and then just the mechanical drilling to eliminate all the recast layer and get the hole. So that's the goal here. Then at the end, it will improve the productivity. It will significantly reduce the machining time, because laser, it will take just fraction of second to make that hole, and then you are using, milling, the hole is already there. So it will take comparatively less machining time, but it will significantly, reduce the heat affected zone and recast layer, right? And also it will improve the profile accuracy, because laser usually doesn't give good profile accuracy. Mechanical machining like micro machining, micro turning, milling or drilling give very good profile accuracy. So here you see that, so first, if you just do the mechanical hole, the first one is good, but it has some bar formation, because as I mentioned, first of all, this process is not very good for difficult to cut material, because mechanical drilling is not good for difficult to cut material. So they are using comparatively, easier material, easier to machine material, but mechanical drilling can end up getting lots of bars. So that's what it says. Now, if you do mechanical finishing after a laser hole in the air, you get, mostly, a good surface finish, but here also, at the exit hole, you have some bars. Then you have mechanical finishing after blind laser in the air, you will have some bar. Mechanical finishing after through hole with oxygen, you get some bar. So it looks like mechanical drilling after the through hole in the air has the minimum amount of bar. But again, if you are working on the micro machining, you know that exit bar is a challenge in micro drilling, okay? So sometimes in order to get rid of that, what they do? They use another material, at the end, so that when you are drilling, you still will have exit bar, but that is on the bottom plate, right? And then you take out the bottom plate, and your target part doesn't have any kind of exit bar. Yeah, so that's the kind of common practice, to do that. Similarly, for composite material, machining composite material is a challenge. Lots of delamination at the end. If you do a drill, at the exit, it will chip up some portion, of the laminate. So how to get rid of that chipping off? If you use a metal piece, they call titanium stack, or aluminum stack, just underneath, that composite, then, and if the interface is very, like how to say, like the interface is, there is good matching at the interface, then when you do the drilling of the composite, it will, like, the exit bar will go into that metal piece. So you can avoid that delamination. So exit bar is a common thing, but as you can see, this process can be used for inclined here. So here it shows some comparison. During the machining of pilot hole, the laser beam was focused for diameter 240 micron. Okay, and it was done at a 30-degree angle. I think here is the information I was looking at. So the cutting forces was reduced by 57%. So that means if you just do the mechanical drilling without any pilot laser hole, the cutting forces is much higher. So you have laser pre-drilling and mechanical finishing. So you see, this is the mechanical finishing actually becomes easier, but if you do just purely mechanical finishing, then it will take much higher. And also number of drill breakage. So drill breakage is an important thing, because as I mentioned, the cutting tools are expensive, right? We don't want the drill to break. So the pilot hole, let me just tell you, even if you do mechanical drilling, like in my manufacturing processes class, so if you want to do 1-inch drilling, okay, how you are going to do that? Which tool you are going to use first? The material which is harder than the workpiece. So what I'm saying, like for example, even if you do mechanical drilling, it is not a safe practice to start with the same drill bit that you want to drill the hole. Yeah, so maybe you can use 0.25, like inch, okay? If you want to go 1 inch, it is very large, okay? So you can do some pilot drill. So 0.25, maybe 0.5. I ask my students to go step by step so that the tool life increases, right? 0.25, 0.5, 0.75, then do 1 inch, right? So very similar here. So if you even, like if you do laser, if you do some pilot drilling, that will help. So the thrust force was reduced by 57% and the torque was reduced by 37%, and gives higher tool life when you use that compound process. And cycle drilling is 50% faster when you use actually compressed oxygen gas instead of the air. So you can further improve that process. Now here it shows some heat affected zone. So it is a section of the laser drill holes. The first one, number A, lots of recast layer. It shows lots of recast layer. And number B, with air, it also shows lots of recast layer. Then if you look at the previous one here, after mechanical machining, there is no recast layer, right? All the holes have smooth and sharp edges. So this is the sequential process. All 4 cases are sequential process, just with different condition, but those are not sequential process, just only the laser process, and you see that it has some heat affected zone here, right? If you look at the inside, you see some heat affected zone. So this is the heat affected zone, right? So some heat affected zone, and when you are using mechanical like drilling followed here, I really don't see any kind of heat affected zone here. Yeah, so not much heat affected zone. So okay. Yeah, so the process capabilities, the compound process can overcome the limitation, of the mechanical drilling, especially for drilling at the angles, acute angles, and it can resolve some of the issues with poor geometry, and also some of the issues with the EDM process, like heat affected zone, recast layer thickness, back wall damage. So those can be removed using the mechanical micro drilling process. Okay, so with this we're done with the compound processes. Okay, so we already, I think, have covered most of the micro scale, hybrid, and compound and assisted machining processes. So tomorrow we'll cover some of the nano machining processes. There are a lot of scope on the nanoscale hybrid, developing nanoscale hybrid machining processes. I remember I was thinking of developing some of the nanoscale hybrid machining processes when I started my academic career, but then the additive manufacturing have come and it becomes a little bit difficult, yeah, but I think there are a lot of scope to apply those at the nanoscale.